Hello, my name is Santiago Aparicio. I am professor of physical and theoretical chemistry at the University of Burgos, ICRAM. And today I'm going to talk about the development of bio-inspired deep eutectic solvents for water treatment and PFAS removal for polluted water. First of all, we are going to talk about the concept of deep eutectic solvents. Deep eutectic solvent is a mixture of two compounds or more compounds in which the development of hydrogen bonding between these two compounds led to the formation of a liquid phase with very different properties to those of the pure components. These compounds had very relevant properties such as suitable viscosity, polarity, density, hydrophobicity or hydrophilicity, and related dynamic properties which can be used for many different applications. The idea is to use the waste oils produced in the work project for the production of this deep eutectic solvent, which will be used for the treatment of polluted waters. These deep eutectic solvents basically are formed by the mixing of these two compounds, leading to the decrease of the melting point, which produce liquid phases with very low melting point. Obviously, the chemistry of these compounds is very wide. We can produce different kinds of deep eutectic solvents combining hydrophilic, hydrophobic compounds, leading to 5 main types of deep eutectic solvents classified according to their physicochemical properties. The main characteristic of these compounds from the viewpoint of water treatment operation is that they can be produced considering hydrophobic properties, compounds which are totally unmixable with treated waters, and these compounds can be produced from renewable sources like natural compounds when mixed with compounds produced from the waste oils, mainly fatty acids. These compounds, these deep eutectic solvents, these kind of materials, can be included into the main principles of green chemistry because they can be used, they can be considered as safer solvents because they are non-toxic, they are environmentally friendly. They are produced from renewable sources or even from waste, like into the work project, and they can be used and designed for degradation. So they led to an inherently safer chemistry, safer compounds when compared with traditional volatile organic solvents. When we want to apply this kind of materials for the treatment of water, we should have clear the problem of PFAS contamination into the environment. Right now, we have a huge problem because of the presence of these compounds in widespread contamination. They have and they show a large human health effect. They are extremely persistent in the environment, in the water, in the soil, in the air, and they are very difficult to remove. So we have a very big environmental problem, a large toxicological problem, and a problem which is very difficult to resolve. These compounds, these what we call PFAS compounds, are a large family of compounds with very different chemistry, but the main characteristic of these compounds is that they present carbon-fluorine bonds. These carbon-fluorine bonds are extremely difficult to be broken because they have large binding energy. And the second point is that we have a huge collection of very different kind of compounds. Right now, we have more than 15,000 compounds of this family, which have been used for very different applications. 4,000 of these compounds are still used in many different applications, and more than 1,000 of them are suffering strict regulations right now. Some of them even has been banned from the use in many different applications. These compounds, these PFAS, are used for a lot of different applications. They are present in cookware, in water, in 540 foams, in many different food packaging compounds. So they are used in a large collection of applications, from transport to electronic applications to food to textiles. So they are present all around us in very different kind of applications. These kind of compounds, for example, show a large market, large chemical market, which led to this large environmental problem in which we have PFAS coming from very different sources, leading to different environmental pathways, contamination via air, via soil, and via water, and leading to many different kind of environmental and safety problems. The key properties of these compounds is their extreme chemical stability, their environmental persistence, their bioaccumulation, they can be present in our tissues for very, very long times. The high mobility, once they are present in the environment, they move from soil to water to air. They show surfactant properties, and right now they show global distribution across the whole planet. Basically, the contamination is present in air, is present in water, and is present in soil in different percentage. Most of the contaminants are present in water, and they show a very complex environmental cycle because of their large mobility. This led to the presence of PFAS in water in concentration in very different ranges, depending if it is groundwater or if it is surface water or if it is drinking water, usually in the range of nanograms or picograms per liter, but they are also present in soils in much, much larger concentration in the range of a microgram, and also in the atmosphere and in biological system, including our own organisms. So this leads to a large contamination, large presence of PFAS in very different kind of water sources. You can see here the data across the world, all the world present relevant points of PFAS pollution in the environment. And in Europe, we have a huge problem because of the presence of these kind of compounds in water, in groundwater, in drinking water, and in wastewater, industrial waters and urban water. This leads to large toxicity problems considering human health. These compounds produce reproductive effects. These compounds affect developmental development. They lead to certain cancer risks. They affect the immune system. They show metabolic effects, and they show in general big organ system effects. So they are present all around us. They show relevant environmental and toxicological problem because they are present in the atmosphere, in the aquatic system, and in the soil system. So basically we have a huge problem related with the presence of PFAS, what we call PFAS in water problem, because at the end we are taking in these compounds in ways such as drinking water. Basically, when we talk about the presence of PFAS in water, we have 4 different kind of problems. When we talk about drinking water, we have concentration usually in the nanograms per liter range. When we talk about industrial water, the waters that come from different plants, we have pollutions 2 or 3 orders of magnitude larger, which led to relevant concentrations of these compounds in surface water and in wastewater that we are using. The range is very different, as you can see in the figure, from nanograms to micrograms or even higher. The main compounds that are present in the environment and in drinking water, and the one that you can see on the slide, we have compounds in wide presence like PFOA, PFOS, PFONA, which are produced by different kind of industrial processes, which are present in water and which we are using in our wastewater and in our drinking water. This led to a strong regulation, both in European Union and United States, which the final objective is to remove the presence of all these compounds into all the water. And in the particular case of drinking water, we have a very strict drinking water directive, both in European Union and both in the United States, in which the limits are in many cases below the 4 or 5 nanograms per liter for the main compounds. So at the end, what we have to do is to remove PFAS from water. What we are doing right now is developing different kind of removal technologies with a special attention to drinking water, but also for wastewater produced for different plants. Right now, we have 6 main groups of technologies: absorption technologies, in which we use different solids or different liquids for remove the PFAS from water; membrane technologies, let's say biological treatment, developing different kind of microorganisms which are able to attack and destroy these kind of compounds; physicochemical technologies based on different kind of absorption, coagulation technologies; and oxidation technologies and thermal treatment technologies. Within the absorption technologies is the ones that we are developing our processes. We are trying to develop new technologies which are competitive with the 2 main technologies right now under development, which is extraction, absorption using granulated activated carbon or ion exchange processes. So the development of deep eutectic solvents, it's in alternatives, an alternative to these absorption technologies, mainly the activated carbon technology, which is, let's say, the state-of-the-art technology right now for the removal of this kind of compounds. The main problem of these technologies is the cost. We must have in mind that a kilogram of PFAS, when it is produced in a factory, may cost between 100 and 2,000 euros or dollars. But removing that kilogram from polluted water may cost several millions of dollars. So the main problem for developing this technology is the cost of the removal technologies, because the removal limits are very, very low. We have to go to the nanograms or picograms per liter in many cases. At the end, this technology, in which we are developing deep eutectic solvents, uses natural compounds or wastes from waste oils produced in the work project to produce deep eutectic solvents, which are used to remove this kind of PFAS in contaminated water. The scheme of the process is the one that you can see in the slide. We have polluted water. We have the eutectic solvent that we have produced using this let's say, with this waste coming from work project. We develop a liquid extraction procedure, and at the end what we have is the PFAS molecules moving from water to the hydrophobic solvents. At the end what we have is the clean water and the PFAS in the extracting phase. For this purpose, what we do is to design specific combinations of the deep eutectic solvents using materials modeling technologies. At the end, what we find is the most suitable combinations of the solvent, which are extremely affine for the kind of PFAS that we are extracting, using a multi-scale theoretical approach in which we analyze the different aspects of the extraction processes, going from the molecules to the liquid phase behavior to the plant design, everything combined in an artificial intelligence approach in order to find the most suitable options for extracting the process. At the end, what we have developed is a kind of tools which allow us to define and to predict the different kind of properties of the materials that we are using, like the physicochemical properties of the solvents, like the ecotoxicological profile of the extraction procedure, because obviously we want to develop a cleaning procedure, but we don't want to create a new process. So all these in silico technologies allow us to screen the whole process in order to develop the most suitable approach. At the end, what we have done is developing a collection of compounds, a collection of solvents, which are extremely affine for the PFAS molecule, which are extremely hydrophobic, then they do not pollute the water, and with very low environmental impact. In that way, we have a sustainable and safe process for the whole extraction procedure. This kind of extraction procedure has a lot of advantages, with extraction efficiency larger than 99%. They are environmental friendly. All these compounds are have negligible volatility, so they do not pollute atmosphere. They are very cost effective in comparison with available technology with activated carbon. They show wide acidity tolerance, because many of these compounds show this kind of behavior which can be tuned considering acidity and basicity of the existence. And at the end, what we can develop, or we have been developing, is a whole extraction procedure in which we have combined the engineering of the process, the design of the final process, with a scaling process in which we use molecular models to analyze the computational properties of the system, the simulations of the liquid phases, and the screening and selection of the whole process, the whole molecules, which are more suitable for the extraction procedures, including the molecular design and the final extraction of the PFAS molecules. At the end, we have established a database of millions of possible candidates, millions of possible PFAS present combined with the deep eutectic solvents, in which we have been able to predict the most suitable combination, affinities, toxicities, suitability of the solvents for the large family of PFAS in combination with the deep eutectic solvents that we are designing. This molecular level picture allows us to infer the most suitable conditions, the molecular level behavior of the PFAS regarding the water phase and the organic phase that we are developing, and at the end, the analysis of the whole properties at the molecular level of the system, the energy, the dynamics, and the nanostructure allow us to develop a whole process using artificial intelligence in which finally we have been able to develop a suitable solvent through the combination of natural compounds and fatty acids coming from the work process, which is suitable for the large database, for the large matrix, the large family of compounds which we are targeting when we treat water for PFAS removal. These compounds are able to be used in different kind of conditions. Our artificial intelligence model predicts us the most suitable condition for extracting the compounds from water phases, and this allows us to develop a final optimal solvent with this combination of multi-scale molecular modeling and artificial intelligence, a new, totally new solvent designed from the waste coming from work project and the natural compounds that we have screened using this theoretical approach, in which the extraction of the PFAS compounds, the large diversity of PFAS compounds, is larger than 99% of the model. As you can see in this slide, the extraction process had been also modeled at an industrial scale, and the final concentration of the PFAS in the treated water is lower than the 10 to the -8 nanogram per liter, which is largely below the restriction limit according to the current regulation. This allows us to develop a technology which different kind of costs, the techno-economical cost of the process has been also analyzed, and the cost can be also decreased when we increase the size of the treatment unit. When we go, for example, from a small pilot plant of 1 meter cubic per hour to large plants like 10 or 100 meter cubic per hour, the cost decrease largely. So the scaling up of the technology has been proved, not only at the pilot plant level or at the laboratory scale level, but also at large TRL. And in this way, we have a technology which is competitive with the available state-of-the-art technology. Basically, when we compare activated carbon with our new technology is in the same range of techno-economical cost with this state-of-the-art technology. So it's a completely alternative technology to the available one. At the end, what we consider is these PFAS which have been removed from the polluted water, from drinking water plants or from wastewater plant. What we do is we do the separation of the PFAS from this extraction phase, from this Deep Eutectic solvent, which can be used again in the treatment plant. And what we do at the end is these PFAS are destroyed using different kind of destruction technology, going from incineration to photocatalytic processes, and at the end we have developed a whole technology removing PFAS from water, recovering the solvent, and destroying the PFAS. So this is a holistic technology in which we consider all the steps of the treatment plant. Basically, in this way, we are able to treat drinking water, wastewater, and industrial water in order to apply it to waters, polluted water, with different levels of contaminations into the matrix, the water matrix that we are considering. Obviously, the conditions can be fine-tuned using our artificial intelligence model for the kind of water and the kind of PFAS that we are considering in our approach. All this research has been carried out into the work project because all the materials that we have been developing are produced using the waste oil that are produced via the work project that we are developing right now. Thank you very much for your attention.